AFL, QBDI And KSE are on a boat. Gabrielle Viala hablará sobre el componente QSE del kernel de Windows y de cómo se puede auditar a fondo a este componente que en ciertas condiciones nos permite modificar llamadas a las API de drivers y modificar el comportamiento mismo de los drivers sin alterar la firma de los mismos o disparar los mecanismos de protección.
So, I'm going to speak about a tiny project I did mostly for fun, but also for to acquire some skills in vulnerability research. But first, who am I? So, as I say, I'm Gabi. I'm reverse engineer at Quarks Lab in France, and most of my time I play with Windows internals. To be honest, I'm quite a beginner, so if you find my project silly, don't laugh too much, please. Okay, so what is it about? Well, I'm going to speak about the Kernel Shim Engine, which is a small component in the Windows kernel. It was added to Windows 8.1, and for some reason, it's not really known, as only Alex Ionescu and Jeff Chappell published stuff on it. But first, let's go for a quick definition, because I'm not sure everyone knows what a shim is. So if you look on the internet, you will find this definition, which basically say that shim is a small patch that transparently intercepts calls to API. It was added to Windows XP in userland, mostly for ensuring retrocompatibility, but also for quick fixing bugs in the MS component. But here I won't speak at all about userland, only about kernel, and since we are in kernel, we won't speak about library or application, but only drivers. And since we are playing with drivers, we can hook other things like the import address table, the driver's callback, or even the IRP measure function. I won't have the time to explain much of the internals of the KSE, but if you're interested, please have a look at Alex Ionescu's talk for Recon to K16, as it's quite well documented. So I will still try to explain how does it work. So you have the shims that are referenced in a database. We will call it the SDB. In this SDB, you will find the name of the components that need to be patched. But actually, the hook implementation are stored in specific drivers that are in charge of giving information about the shim to the KSE. So I'll go graphical because it's more convenient for explaining this stuff. So here you have the KSE function, that means all the mechanism. The DB I presented a few slides before, and the internal structure used by the KSE and that are in memory. So when a driver is loaded, the KSE is in charge to know if he needs to patch it or not. So first, he tried to look in his internal structures to know if he already knows these drivers. If not, he will retrieve the shim that can be applied on the drivers in the DB. Then look for the shim in its internal memory, internal structure, because a shim can be applied on different drivers. If he doesn't know the shim, he will need to load the drivers that store all the hooks, and these drivers will register the shim in memory. Then the KSE will be able to retrieve the shim and apply the hooks when it's needed. So actually that's pretty simple. Here I won't speak about this mechanism, but I will focus on the SDB. So as I said, that's a database that references all the shim available on the OS. It's actually a file on the disk that you can find in the Windows App Patch folder. That's, in fact, the SDB uses the same format as all the SDB used in userland, so it's quite well known. Except that you have new entries like quicks and so on. And the structures kind of look like the drawing here. So you have three different sections. The first one is for indexing, so you have a lot of hash map in it. The second stores all the data. And the third one is used for storing all the strings that are referenced in the second section. Here you may want to remember the first section, as we are going to speak about it later in this talk. So, why it's interesting to speak about the SDB? blah blah. Ooh. Okay, so long hair, not good. So what did I say? Okay, so the SDB is not signed, so anybody with administration right can modify it as they want. Plus, searching in file imply using a parser, and a parser is still it's always good to play with. And in addition, if you look at the code of this parser, you will find some similarities between between the parser and the parser used in userland. So it seems like Microsoft adapted the parser from userland to kernel. This can lead to new bugs. So yeah, I was thinking it was an interesting attack place. So, as I wanted to try fuzzing something for the first time, I decided to use it as my target. It was just perfect. Well, not really perfect, because remember, we are in kernel, and that's not really convenient to fuzz it. Besides, the parser is used only when a driver is loaded, and the process is quite slow, so it's not really optimum as well. I was quite lazy, so I didn't want to create hooks to isolate the interesting function. So I decided to adapt the parser from kernel to userland. So yeah, that's my first step. So for this section, this step, I extracted the function from nts-kernel.exe and replace all the kernel function to userland equivalent. Overall, it's quite straightforward, but quite long, and sometimes you don't have equivalents, and that can become painful. Hopefully, my parser was quite standalone, so I didn't have too much trouble. The only thing was for logging, so I decided to remove this this function because they weren't really in my target. Okay, so when you have that, you can you can create a small function to verify that your parser is still working. And hooray, it's working. I was happy. And I wanted to fuzz it. So when you're not really accustomed to fuzz and you try to think about a tool, the first one you bump into is AFL. Plus it gives a lot of good results with fuzzing parser. So I wanted to try it. The thing is, if you already know AFL, you have two drawbacks for me, for my project. First one, it only accepts source code as input. And the second one is, well, it doesn't really work on Windows. So the first issue is not really an issue because you can handle it by using a DBI. For the records, that's a method of analyzing the behavior of a binary at runtime. In fact, you inject instrumentation code inside the binary, so you can observe any state of the program when it's running. The good thing is, at work, we are developing our own DBI, which is called QBDI, which is open source, based on LLVM, cross-platforms, cross-architecture, and so on. And plus, it can be plugged to other tools. So it was perfect for me. I decided to use it, and first problem solved. The second, well, that's silly, but I was thinking, okay, I adapted kernel code to userland, so why not go further and adapt it to Linux? So yeah, that's my answer. I decided to adapt it to Linux. And right now you may wonder why I didn't use WinAFL. Well, I knew this tool. It's a fork that actually uses an instrumentation engine, and it's working on Windows, so it would have been just perfect for me. So yeah, why? Well, the first thing is, actually we needed to beta test QBDI on a real test case. And the glue between AFL and QBDI didn't work on Windows at the moment. So I couldn't use WinAFL. The second thing is, I kind of wanted to port kernel code on another platform. The challenge seemed really cool. So yeah, why not? And last but not least, actually my coworkers are sadists. They wanted me to learn the hardware, so they pushed me in that direction. So yeah, that's why I didn't use WinAFL. Okay, step 2. Well, porting Windows code on Linux. I was thinking, I'm kind of stupid, so I was thinking, okay, I adapted from kernel to userland. So from Windows to Linux, it's not really hard. Well, yes, it is. In fact, when you finish to remove all the Windows-only function, you just bump into differences between Linux and Windows that are quite painful to handle. For example, you have the calling conventions, which are different from Linux to Windows, and you have to create a small trampoline to translate the API. It's not really hard. As you see, there's one example here. It's only 3 lines of code. But you need to do that on any call to native function, native call to native function. So, yeah, it's a bit painful, in fact. In addition, in fact, this is not finished. Linux and Windows are using the same type, but actually they are not the same type at all. Well, for example, in my parser, there was a lot of white string. And a white char in Windows is not the same as a white char on Linux. For example, Windows uses 2 bytes to encode it, and Linux is 4. So if you're using white string created on Windows with a function with function on Linux, it doesn't work at all. So yeah, I didn't find anything better than rewriting the string function. So it was awful, really. Don't do that. Okay, when you finish, you can at least fuzz. Yeah, cool. And at this point, I was thinking, okay, I had so much problem, it would be awful to just try to instrument the code because I don't have any clue about how instrumentation engine is working. I never tried instrumentation as well, so yeah, I was quite stressful for this part. Actually, nope. I don't know for any other instrumentation engine, but using QBDI, it's only 30 lines of code, and it's really straightforward. So, yes, cool. Plus, I decided to use libdislocator to detect small memory corruption. So this part was also quite easy as well. So, yeah. I tested my fuzzer. It was working. Fist bump with myself. Cool. Okay. So now it's time to create a corpus because AFL needs a valid test case to be very efficient. And the thing is, the SDB that are already on the EOS are a bit too big, and it will be really, really slow to just feed them to AFL like that. So it's better to minimize them with AFL CMIN and AFL TMIN. There are 2 tools provided by AFL, with AFL. The thing is, even with that, you're not sure to have a really big corpus as the SDB are intended to be used and not intended to be fuzzed. So it's better to also create new minimal SDB, which is really simple because the format is already well known. It's not documented if I remember correctly, but it's quite known. So you can easily define the format and create a builder. So okay, you have your corpus. You can fuzz, and this part I won't really have the time to explain it. Besides, it's not really different from using AFL with QEMU, so it's not really interesting. Just I start in my fuzzer, and at some point, it's better to stop the fuzzer to remove, to refine the corpus created by AFL. This way, you can remove very redundant and not really useful sample, and maybe optimize a bit to find new passes and crashes. So I let it run for something like 1 week or something like that. And at the end, I found a lot of crash, something like 700, so I was really happy. But I wasn't sure that they was usable in real world because I adapted a lot my parser. So I wanted to verify the reproducibility on Windows 10. and retrieve the crash dump. So I created a small script because there's a lot of crash and didn't want to do it by hand. That basically take a network share, put a file produced by AFL, spawn a Windows and VM where where special pool flag is activated, so you can identify memory corruption issue. Plug a debugger, move the SDB on the VM, reboot the VM because most of the drivers are loaded at boot time. Wait for a crash and retrieve the crash dump and compute some hash to quick triggering the crashes. And do it again and again and again on every file. So I went from 700 crashes to 165, which is really cool. So, sorry, it was French. Except that almost all the crashes are similar if you triggering them with the hashes. And in fact, most of them have almost the same root cause. And I will try to explain one, the root cause. In fact, the bug I found was because of a faulty memcopy in a function named SDBP binary search first. This function is used to perform a binary search on a SDB hash map. Remember the first section of the SDB. In fact, a quick debugging shows that it was wrong in the first row of the binary search. And in fact, the issue is because the number of elements of the hash map given in parameters is totally wrong. The thing is, this number is retrieved by another function above, which is SDB get tag data size. And this function basically just retrieves a field in the SDB that we control, but checks if the value is valid or not. And if not, it's returned -1. So there is no issue there. So the issue is, in fact, between the two functions. And it's because of this 5 lines of code for time instruction, sorry. And I will go quick here. In fact, there is no validation. So yeah, it's lead to out-of-bound issue. And oops, the thing is, it's not exportable because we don't have a real control over the input. We don't have any control over where the value is written. The SDBP binary search first function return an offset that is checked a bit later. So I didn't find any way to exploit it. Sorry. So, in conclusion, and I'm on time, yeah. I found out that porting Windows kernel code on Linux is not fun at all, but quite painful. The thing is, it still gives some results, so I will probably do it again. But next time, first, I won't listen my coworkers, ever. The second is that there's a lot of steps that are really long and painful, so I will try to automate them. And at least I will use WinAFL, because no, I won't adapt on Linux, never again. So yeah, that's it. Any question?